Good afternoon, all of you. Yeah. Mm, so, welcome to the session of grade class for the subject of analog circuits. Okay. Now, actually, this is very important subject in the ECE branch. C branch students, analog circuits, digital circuits. Okay. Um, so, basic concept for this analog circuits is actually that is EDC, electron devices and circuits. Okay, electronic devices and circuits, and this is the extension of electronic devices circuits subject. Okay, analog circuits, or we can call analog electronic circuits. So in this unit, sorry, in this subject, we'll have different topics like feedback amplifiers. Okay, small signal amplifiers, small signal also high transfer amplifiers, multi-stage amplifiers. Okay, power amplifiers, tune amplifiers. Okay, okay, and the diode circuits. Okay, these all comes under this analog circuits. Okay, and op amp applications, operational amplifiers. Okay, operational amplifier. Okay, this all topics comes under this analog circuits, right? Now, so first of all, we'll discuss about this small signal high frequency transistor amplifier models. Okay, small signal high frequency transistor amplifier models. Actually, you all know that about amplifiers or amplification concept. Okay, so what is amplifier? So, which is a circuit which converts weak signal into strong signal. That means which strengthens the input signal. Okay, that circuit is called amplifier circuits or simply amplifiers. And the process of converting small signal into large signal is called amplification. Okay, so for this amplification purpose, the major element and very important element is transistor. Okay, transistor. So transistor is an electronic component or device which behaves switch, either a switch or which performs amplification also. Okay, there are so many applications for a transistor. It acts like a on switch, it acts like a off switch, and also it can be used as an amplifier based on different conditions. Okay, so I will explain one by one detail. Okay, before discussing about this transistor, first of all you should know about the diode concept. Okay, diodes. So the diode, the name indicates itself. Diode has two terminals. Okay, two terminals. Those two terminals are, one is positive terminal, another one is negative terminal. Okay, positive terminal is called anode, and negative terminal is called cathode. You already studied about these concepts. Just I want to revise those topics for a few minutes. Okay, right. So diode is a two-terminal device, and the function of the diode is it allows the current only in one direction, not bidirection. Okay, it allows the current only in one direction. Okay, and the applications of diode is it acts as a on switch in forward bias, it acts as a off switch in reverse bias. Okay, so now what is forward bias and reverse bias? Okay, we have two terminals for diode, one is anode and cathode, and that is a positive terminal and negative terminal. If we connect the p-type terminal to positive and n-type semiconductor to negative terminal of the battery is called forward bias. Okay, now we are applying bias to the diode. Okay, okay, if you give p-type if you connect the p-type semiconductor to positive terminal and n-type terminal to negative terminal of the battery is called forward bias. Generally, what is meant by biasing? Biasing means just connecting one external DC voltage source. Okay, if we connect one external DC voltage source to a device is called biasing. Okay, based upon the polarities, the biasing is classified into two types. One is forward bias, another one is reverse bias. Okay, now what is forward bias? So P-type semiconductor is connected to positive terminal, and N-type is connected to negative terminal of the battery. This is called forward bias. And reverse bias means just connecting reverse mode. Okay, connecting P-type semiconductor to negative terminal and N-type semiconductor to positive terminal is called reverse bias. Okay, if you understand these concepts like diode concept, it is very easy to understand the transistor part also. Okay, so this diode part is very basic for the our electronic subjects. Okay, so this is about difference between forward bias and reverse bias. I think I hope you understood this difference between forward bias and reverse bias, right? And the next one is semiconductors. These p-type semiconductor, n-type semiconductor, this diode is came from semiconductors actually. Okay, semiconductors. We have basically three types of materials: semiconductors, conductors, insulators. Okay, conductors, insulators, semiconductors. So conductor. Okay, conductor means which allows the charge carriers completely. Okay, and for example, if you connect the conductor to bias, there is a huge movement of charge carriers. That means you will get the maximum current. That is called conductor. Okay, insulators. It doesn't allow the charge carriers. Okay, it does not allow the charge carrier. That means less conductivity. I mean low current. Like examples are wood, okay, plastic, okay, and fiber. Okay, these are all the examples for insulators. And conductors examples are gold, okay, aluminum. These are all metals. These are all the conductors. There are some examples. Coming to semiconductors, very important. Semiconductors. So semi means partially, okay, which partially allows the charge carriers. Okay, that means it is better than insulator and lesser than conductor. The conductivity range between insulator and conductor. Okay, so this is the difference between conductors, insulators, and semiconductors. Okay, and semiconductors examples are, what are the examples for semiconductors? Germanium, silicon. These are the very important materials for semiconductors. Silicon and germanium. Now, among these two, which one is better? Silicon is better. Already you have studied in EDC subject in 2-1. Okay. Among silicon and germanium, which one is better? Silicon is better than germanium. Why silicon is better? For silicon, the stability is very high when compared to germanium. That is one factor. And the second point is and availability. It is easily available in our nature. Okay, that is another advantage. And one more advantage for silicon is cost. The cost is very less. So these are the advantages for silicon material. That's why when compared with aluminum, silicon is very much better in the usage of electronic components. That is the difference between silicon and germanium. Okay, and also these semiconductor silicon and germanium having four valency electrons. Silicon having four valence electrons, and also germanium also has four valency electrons. Okay, right. So silicon is very useful material in our electronic circuits components. Okay, so what are the advantages of silicon? Stability high. Okay, cost is also less, and also availability also good. So for this reason, we are preferring silicon than germanium. Now, in diodes also, we have silicon diode, germanium diode, and also so many other types of diodes. That is Gina diode, okay, photodiode, light emitting diode, okay, Okay, these are all the different types of diodes available in our electronic components. Okay, now if we connect the diode in forward bias, so what is forward bias? Already I have told about forward bias. Connecting p-type semiconductor to positive terminal, n-type semiconductor to negative terminal of the battery is called forward bias. If we connect, Hindi. Okay, so this is about the introduction of semiconductors and diodes. Okay, now I am going to explain about the electronic circuit analysis concepts. Okay, let's see. Yeah, so this is the first unit in our analog circuits, that is small signal high frequency transistor amplifier models. Okay, so small signal high frequency transistor amplifier models, and these are the topics which I am going to cover in this first unit. Okay, so we have two sections. One is BJT and second part is FET. So bipolar junction transistor, the first section, and second one is field effect transistor, FET. And BJT, these are the topics. Transfer at high frequencies, hybrid by common emitter transistor model, hybrid by conductances, capacitances, validity of hybrid by model, determination of high frequency parameters in terms of low frequency parameters, CE short circuit gain, current gain with resistive load, cutoff frequencies, frequency response and gain value product. And this is about FET, and the second part is FET, analysis of common source, common drain in high circuits. So these are the topics, right? So in this section, the major important element is two-port network. See, okay, this is two-port network concept. So we have two ports. This is input port. This is output port. And the input port, we have I1 input current. V1 means input voltage. Similarly, for the output section, I2 is output current. V2 output voltage. So from this figure, we can calculate four H parameters. This is very, very important. Hybrid parameters, or simply we can call it as H parameters. We have four H parameters. Okay, those four parameters are input impedance, output admittance, reverse voltage gain, and forward current gain. Okay, so these are the four H parameters: H11, H12, H21, and H22. So what is H11? Input impedance with output short circuited. Okay, so H11 means input impedance. The condition to calculate this H11 is the output must be short circuited. Next, second one, H22, output admittance, and the condition is input must be open circuited. Next, H12, this is called reverse voltage gain. The condition is input is open circuited. Similarly, H21 means forward current gain, the output is short circuited. These are the four H parameters. So these four H parameters are very, very important to analyze the transistor circuits. Okay, and H11 input impedance, the unit is ohms. H22 input is output admittance, H22. So unit is ohm inverse or mhos, and H12 or H21. So these are dimensionless. That means so there are no units because H12 is forward current gain, H21 reverse voltage gain. So for gain there is no units. Okay. Now, so these are the notations using transistor circuits. So HIE. So HIE means input impedance. Okay. HOE. Okay. HOE. output admittance, HRE reverse voltage gain, and HFE short circuit current gain. And these are the equations for voltage and current. Okay, and this is H parameter equivalent model, standard H parameter equivalent model of BJT transistor. Okay, so in this circuit, what are the elements presented? This is HI resistor, and the current flowing through HI is HI into I1, and this is voltage source, HR into V2, and this is output section, this is input section, this is input section, this is output section, and this is current source, HF into I1, and admittance HO into I2. This is resistance. So this is H parameter equivalent model of BJT. Now let's take common emitter amplifier. Okay, so we have three amplifiers, three BJT amplifiers: common emitter, common base, common collector. Okay, so common emitter means, so this is common emitter amplifier. In common emitter amplifier, base is the input terminal, collector is the output terminal, emitter is common terminal, or we can ground this emitter terminal. So this is common emitter amplifier. Okay, so in common emitter, base is the input, collector is the output. This is load resistor. Okay, now if we draw the H parameter equivalent model for this CE amplifier, so this is the figure. So this figure is called H parameter equivalent model of common emitter amplifier. Okay, and in H parameter model, hybrid models also we have two types. One is exact hybrid model, another one is simplified hybrid model. This is called exact hybrid model. Okay, this figure is called exact hybrid model of common emitter amplifier. Okay, so in this figure, what are the elements presented here? HIE, because it is a common emitter configuration. That's why I mentioned here HIE, input impedance of common emitter. And this is voltage source, HRE into VCE, and this is current source, HFE into IB, and this is output impedance, HOE, and this is load resistor. So from this figure, if you write the H parameter formulas, these are the H parameter formulas. HIE is equal to, so what is HIE? Input impedance. So input impedance means the ratio of input voltage to input current by keeping output voltage constant or zero. Okay. If we want to calculate HIE input impedance, the formula is VBE by IB by keeping VC value 0. Okay. Similarly, HRE. HRE means reverse voltage gain. Change change in input voltage by change in output voltage. Okay, by keeping IB 0, input current 0. Next, HOE, output admittance. Output admittance means output current by output voltage, and the condition is IB equal to 0. And similarly, HFE is equal to IC by IB. So what is HFE? Forward current gain. Output current by input current. Ratio of output current by current in input current, VC value 0. So these are the standard expressions for H parameters. Okay. Now let's take one simple example. See, this is HIE, input voltage by input current. So, okay. Now you substitute the value. HIE is equal to 0.2 volts. So here VBE means, so HIE is equal to VBIB. So here I substituted VB value is 0.2, IB value 50 microamperes. So what is the value? 4 kilo ohms. Okay. Similarly, HFE, IC by IB. If you substitute IC and IB values, approximately we will get 100. Okay. These are the some relations. HRE, zero point 0.2 into 10 power minus 3. Okay. And input resistance formula. Okay. There's some important next voltage gain expression. And this is current gain expression. AI is equal to minus HFE by 1 plus HOE into RL. Okay. This is the current gain expression in common emitter amplifier in exact model. Okay, and again A is equal to minus HFE by 1 plus HOE into RL. Next, this is voltage gain expression. Minus HFE into RL by HIE plus RL into HIE HOE minus HFE into RL. Okay, so this is about common emitter amplifier. So these are all the common emitter amplifier formulas. Next, we see the common base amplifier. So this is common base amplifier. Okay. So in common base, what is the input? Emitter is input terminal, collector is the output terminal, and RL means load resistor, RS is source resistor, input resistor. Okay. Here the base terminal is grounded. Okay. Now these are the formulas. So just like common emitter amplifier, the formulas also same here. Input impedance is equal to change in input voltage by input current by keeping output voltage zero. VV by IV at ECB equal to zero. Okay, if you substitute the values, basic values, you will get the answer like this. So HFB typical value minus 0.99. Okay, next HOB 7.72 10 power minus 8 ohm inverse, or we can write MOS. Next HRB means reverse voltage gain 37 into 10 power minus 6. Okay, and these are the current gain formula minus HFB by 1 plus HOB into RL, and voltage gain is equal to minus HFB RL by HIB plus RL into this one. Okay, already you know these, you know all these formulas. Okay, next one, common collector amplifier. So here common collector means base is the input terminal, emitter is the output terminal. Emitter is the output terminal, collector is the common terminal. Okay, so in common collector amplifier, whatever the input you are applying at the input side, the same output you will get the output side. That means input is equal to output. That's why in common collector amplifier, always the gain value is approximately 1. Okay, the gain value is approximately 1. That's why the CC amplifier is also called emitter follower. Okay, emitter follower or unity gain amplifier. Okay, and this is the equivalent model of CC amplifier. CC amplifier. Now, so up to now we have discussed about the small signal low frequency case. These are all the figures, small signal low frequency. Let's see about transistors at high frequencies. Okay, transistor circuits at high frequencies. So if we consider high frequency case, the H parameter model is not suitable because the H parameter analysis is applicable only for low frequencies. Okay. Now, if we're applying high frequency, the H parameter is not suitable. Definitely, we have to use hybrid conductance model or hybrid pi model. You can call it as hybrid pi model. So this is the basic figure. Okay. This is the basic figure, hybrid pi common emitter transistor conductor model. So what are the elements here? RBB. So RBB means base bearing resistance. Okay. Next RB dash E input resistance. Next RB dash C feedback resistance. Next RCE output resistance. And this one GM into VB dash, it is a current source. And these two are the capacitances. This is the diffusion capacitance. This is the transient capacitance. So this is the basic figure of common emitter concept at high frequencies. Remember, at high frequencies, not low frequencies. Okay, and this figure is also called Gioccoletto model. See here, this hybrid pi model is also called Gioccoletto model. Okay, so here the names: RBB dash base fitting resistance, RB dash E internal base mode or emitter resistance, RCE collector to emitter resistance, influence capacitance or interbase junction capacitance. Next, RB-C feedback resistance. GM means transconductance. Just a minute. Okay, and these are the components in hybrid pi model. Okay, now and hybrid n parameter values. So IC value, these are some standard values. IC is equal to 1.3 milliamperes, and if you substitute IC is 1.3, you will get the transconductance 50 millimos. Okay, like this, these are the standard values. RBB dash base bearing resistance is 100 ohms, RB dash 1 kilo ohm, RC 80 kilo ohms, and CC 3 picofarad, CE 100 picofarads, RB dash 4 mega ohms. Now, determination of hybrid by conductances. How to calculate these, how to determine these hybrid by conductances. So these are the derivative part. Okay, the first one is trans conductance, or another name is mutual conductance, GM. So to derive this factor, we consider this figure. Okay, so from this figure, I am writing these formulas. IC is equal to IC naught minus alpha into I. So in this, IC means total collector current, IC naught is reverse saturation current, alpha means current again, and I means emitter current. Okay, by deriving these equations, so see, these are the different steps. Okay, and at the end, you will get this formula. GM is equal to minus IC by VT, but the current should be always positive. That's why I put modulus. Okay, GM is equal to mod IC by VT. Transconductance GM is equal to mod IC by VT. If you substitute IC is equal to 1.3 milliamperes, you will get, see, for two different IC values. If IC is equal to 1.3, GM will be 0.05 mos. If IC is 10 milliampere, GM will be 400 millimos. Similarly, input conductance, GB dash E. Okay, input conductance GB dash E, or we can write GB dash E is equal to 1 by RB dash E. So how to calculate this GB dash E? So for this, you consider this figure, and these are the derivative part. Of course, this is not important for you, this gate classes. Just I want to show these equations. Just all of you please go through these equations, and at the end you will get this is the formula. GB dash E is equal to GM by HFE or IC by HFE into VT. Okay, this is the equation of GB dash C. That means input conductance. Similarly, feedback conductance GB dash C. So GB dash C formula HRE into GB dash E. Okay, GB dash C is equal to HRE into GB dash E. Okay, or another formula is HRE by RB dash E. Okay, next base spreading resistance RBB dash. So base spreading resistance means this resistance is connected between B and B dash, internal node and external node. That's why it is called base spreading resistance. This base spreading resistance formula is HIE minus RB dash E. These formulas are very important to analyze a hybrid pi model for common emitter amplifier at high frequencies. This is only for high frequencies, not for low frequencies. Next, output conductance. GCE. So the output conductance GCE is equal to, this is the formula, HOE minus HFE into GB dash C. Okay. Okay. Now, so what are the elements we have discussed now? Output conductance GCE, HOE minus HFE into GB dash E, RBB dash base bending resistance, HIE minus RB dash E. Next, another one is feedback conductance, GB dash E is equal to HRE minus GB dash E, and so on. Okay, this is about hybrid by conductances. Let's hybrid by capacitances. The diffusion capacitance and transition capacitance. We have two types of capacitances. One is diffusion capacitance, another one is transition capacitances. So diffusion capacitance is it occurs in forward bias, and transition capacitance occurs in reverse bias. Okay, diffusion capacitance occurs in forward bias, and transition capacitance occurs in reverse bias. And this is the formula. Cc is inversely proportional to Vce to the power of n, where n is equal to 1 by 2 for observed junction, n is equal to 1 by 3 for graded junction. Okay, so Cd is equal to transition capacitance, Cd is equal to diffusion capacitance. Okay, but practically CDE is very much greater than CDE. Okay, next, validity of hybrid pi model. This validity hybrid pi calculated model be valid for frequencies less than the unity gain frequency. Okay, now in terms of low frequency H parameters. So this is the figure. This is hybrid pi model. I mean, high frequency model uses low frequencies. This is low high frequency. This is low frequency. When you compare these two, we can write these formulas by comparing these two figures, first one and second one. Okay, we can write these relations. See, Gm is equal to mod IC by Vt, Rb dash HFE by Gm. Okay, and from this equation we can derive common emitter short circuit current gain. Okay, these are all the derivative part. There are derivative part, and this is the formula. This is the formula. Short circuit current gain A is equal to HFE by square root of 1 plus F by F beta whole square. This is short circuit current gain. Okay. Yeah. Next, Miller's theorem. Miller's theorem means if any impedance is connected between input and output, then only we can use the Miller's theorem. Okay. See, here the impedance RB dash C and CC is connected at the feedback section. That's why I could modify the figure like this. Okay, this is the figure. This is the modification of the figure 1 figure, this figure using Miller's theorem. Okay, and this K means gain. So K is nothing but gain. The formula is minus Gm into R. And here we have different frequency parameters. Frequency Ft means it is a frequency at which short circuit common gain becomes unity. So wherever the frequency gain becomes unity, that frequency is called Ft. Next, another parameter is F beta. F beta, and F beta formula is this one, Gm by Hf into Ce plus Cc, and relation between Ft and F beta is this one. Ft is approximately Hf into F beta. Very, very important relation. T is approximately equal to Hf into F beta, and these are all the relations in short circuit current gain. Next, gain bandwidth product. The product of gain and bandwidth is called gain bandwidth. Suppose if the gain is high, bandwidth will be low. If the gain is low, the bandwidth will be high. But anyway, the gain bandwidth product is always constant. Okay, that is a concept. Next, FET amplifiers. So up to now, what we have discussed? Okay, so common emitter amplifier at high frequencies. Okay, common emitter amplifier at high frequencies. Okay, so in this, what we have seen different formulas, different frequency parameters. Okay, H hybrid by conductances, hybrid by capacitances. Okay, and short circuit current gain and current gain derivation using Miller's theorem. Okay, current gain derivation using Miller's theorem, and these are the equations. Okay, for parameter to calculate parameter of beta, these are the some cases. A is equal to 1. See, Ft is the frequency where the short circuit current gain becomes unity. That means if A is equal to 1, this value must be is equal to 1. From this, we can simplify this equation. Okay, we will get this formula. Okay, Ft is approximately equal to Hf into F beta, and from this Ft is equal to Gm by 2 pi Ce. Okay, and these are all the derivative part. Next, this is gain bandwidth product. So, what is gain bandwidth product? This is a measure to denote the performance on amplifier circuit, and is also called figure of merit. So, gain bandwidth product is also called figure of merit. Okay. So, any amplifier circuit must have large gain and large bandwidth. For certain amplifier circuits, the mid-band gain may be large but not bandwidth, or vice versa. Okay, and that means the gain. So just now I told. So suppose if the mid-band gain is high, the bandwidth will be low. If the mid-band gain is low, the bandwidth will be high. Okay, if you multiply this gain and bandwidth, so the value must be constant. Okay, different amplifier circuits can be compared with different parameters. Next, FET. So till now we have discussed about BJT concepts, bipolar junction transistor concepts. Okay, so in BJT we have common emitter amplifier, common base amplifier, common collector amplifier. But in this unit we have seen only common emitter amplifier at high frequencies. common emitter amplifier at high frequencies. So at high frequencies, we can use hybrid pi model. Okay, what is another name of this? Geo-collector model. Okay, okay. Now coming to second one, FET amplifier concepts. Field effect transistor. So just like BJT, we could use the original small signal model for low frequency analysis. Okay, for FET also we can use the same figure. Okay, so FET is a unipolar junction transistor. Unipolar junction transistor. Okay, why it is called unipolar? Here the current conduction is due to only with majority carriers. But in BJT, the current conduction is due to both majority and minority carriers. Okay, so that's why BJT is called bipolar junction, but if it is a unipolar junction, here the current conduction is due to only majority carriers. Now, like BJT, in FET also we have three different amplifiers configurations. We can say those are common source amplifier, common drain amplifier, common gate amplifier. Okay, so what amplifiers we have in BJT? Common emitter, common base, common collector. Just like that, in FET also we have these three amplifiers: common source amplifier, common drain amplifier, common gate amplifier. Okay, so in common source amplifier, okay, gate is the input terminal, drain is the output terminal. Okay, gate is the output terminal. Gate is the input terminal, drain is the output terminal. Okay, and this is high frequency common source amplifier figure. See in this figure what are the elements presented here. So R means resistance, RG gate resistor, VGS gate source voltage or voltage in gate and source, and CGS gate source capacitance, CGD capacitance between gate and drain. Okay, and this is current source, GM into VGS. GM into VGS. So GM means trans conductance, VGS means voltage. The product of conductance and voltage gives current. This is the current. Next RDS, drain source resistance. Because this resistor is connected between drain and source. That's why it is denoted as RDS. Next one, capacitance. Okay, drain source capacitance, which is connected between drain and source. And this is total resistance, RD parallel RL. Okay, RT means drain resistance, RL means load resistance. The parallel combination of these two gives this resistance. Okay. Now we may simplify the small signal circuit by making the following approximations and observation. See what are our approximations? RDS is usually larger than RD parallel RL. So we have to assume these points. Okay. So, so the parallel combination is dominated by RD parallel RL. Okay, and RDS may be neglected. If this is not the case, single equivalent resistance may be defined. Okay, of course, it is not mandatory to have all these resistors at the output side. Sometimes we may have only single resistor also. Then only we can consider that single resistor. Suppose if two, three, or four are any resistors, how many resistors are connected at the output side? We can consider the parallel combination of all resistors. Okay. So in the figure, what you observe, this resistance is the parallel combination of RD and RL. But in some figures, we may have only RL or we may have only RD. Okay, or more than two or three resistors. So at that time, uh, we can calculate the total parallel resistance. So that gives the output resistance. Okay. Again, we are using Miller's theorem, Miller's concept. Just a minute. Okay. Now, so we have seen this high frequency response of common source amplifier. Okay. So from this figure, these are the different equations like the Miller capacitance CM1, that is Miller capacitance 1, CM2 is Miller capacitance 2. And these are the formulas CGD. So what is CM1 formula? CG is equal to 1 minus AB. So from input circuit, we can write these equations. Miller capacitance 1 is equal to CGD, that means gate drain capacitance. CGD means gate drain capacitance into 1 minus AV means voltage gain. Similarly, CM2 means CGD into 1 minus 1 by AV. This is from the output circuit. Similarly, here CDS is very small, so the input contribution of this capacitance may be considered to be an open circuit and may be ignored. Okay, so from this figure, so after simplification of these equations and this is the input capacitance formula. Cn is equal to Cgs plus Cm1 is equal to Cgs plus Cgd 1 minus A. So in place of Cm1, I substituted this one Cm1. Okay. Similarly, Cn Cgs plus Cm1. Again, I substituted this formula. So the parallel capacitance in the output circuit CDS and CM2 may be combined to a single equivalent capacitance of value. So Cout is equal to CDS plus CM2 and CDS equals what is CM2 value? So here CM2 means this one CGD into 1 by 1 minus 1 by AV from the output circuit. So CDS plus CGD into 1 minus 1 by see here AV means voltage gain minus GM into RD parallel RL. This is for common source amplifier. Okay. Now, okay, and this is the simplification figure. After simplification, the previous figure, this is the main figure. This is the main figure. If you simplify this figure, you will get the this alternate figure. I mean another simplification figure. Okay, so from this figure, these are the equations. Okay, frequency terms omega is into frequency. So 1 by Cn into R by Rg. From this, so what is omega? We can write 2 pi Fh. Okay, then Fh is equal to this one. Okay, next. And high frequency common source, another figure. Characteristics of common drain. Okay, so till now we have seen common source amplifier. Okay, we have seen common source amplifier. Let's see common drain amplifier. So in common drain, gate is the input terminal, source is the output terminal. So gate is the input terminal, drain is the output, source is the output terminal. And what are the characteristics of this common drain? Voltage gain, voltage gain approximately 1, high input resistance, low output resistance, and is a good voltage buffer. Okay, it can be used as a good voltage buffer. Okay, okay. Now, so in BJT also, like CD and BJT also, we have common collector amplifier. There, the common collector amplifier is also called emitter follower. Like that, CD amplifier is also called source follower. This is very, very important point. Remember this. So common drain amplifier is also called source follower. Okay, why this is source follower means in common drain amplifier, what is the output terminal? Source. What is the input terminal? Gate. That means the output measured at source terminal follows the input terminal. Okay, that means whatever the input you are applying at the source terminal, gate terminal is same as the output terminal. That's why this is called source follower. So that the gain value is always 1. Okay, that's why it is called source follower. And what are the other characteristics? Voltage gain 1 over high input impedance, low output resistance, and it is used as a good voltage buffer. Okay, good voltage buffer. Okay, next. And this is the equivalent model, high frequency small signal model for common drain amplifier. Okay, see, this is CGD, the gate drain capacitance, CGS, gate source capacitance, current source. Okay, and these are the additional capacitors, CDB, CSP. Okay, CSP. Just a minute. So this is high frequency small signal model. Okay. Right. Now, after simplification of this figure, after simplification of this figure, we will get this figure, and these are the different equations. Okay, AV into CGS, RL by Rout plus RL, and it's equal to GM into RL by 1 plus GM into RL. So these are all the equations based on Miller capacitance, Miller's theorem. Okay, okay, based on Miller's theorem. Cm is equal to, that means Cm stands for Miller capacitance. Okay, Cm stands for Miller capacitance, which is equal to CGS into 1 minus AV into CGS. Okay, and after simplification, so these equations we are getting. Okay, and RT, RCGB, these are all the equations, and this is a frequency, 3 dB frequency. Okay, and see this figure, this is BJT amplifier. Okay, so this is about the first unit topic, BJT and effect high frequency analysis. Okay, so this is a high frequency of common source, and this is about the first unit. So once again, let's see what topics we have discussed till now. So H parameters, types of H parameters. We have four H parameters: HIE, HRE, HOE, and HFE. Okay. Then common emitter BJT equivalent model, common drain equivalent model, sorry, common base, common collector, and formulas, and voltage gain, current gain. Similarly, common base amplifier and those H parameter values. Okay. Similarly, common collector. Here the main point is another name of common collector is emitter follower, and this is the circuit in common collector. Base is the input, emitter is the output. C. Okay, and actually exactly similar to FET amplifier. Which one? Common drain amplifier. Common drain, in common drain, gate is the input terminal. Okay, and source is the output terminal. So there common drain is also called source follower. Similarly, this common collector is also called emitter follower. Okay, and this is the equivalent model, H parameter equivalent model. Okay, these are the standard values. And high frequencies, at high frequencies we can use this hybrid pi model. Okay, hybrid pi model. Okay, and these are the different components: RBB standard values, hybrid conductances values. Okay, it's hybrid conductance, collector current, transconductance value, and formulas, and standard values. Similarly, input conductance equation, circuit diagram, formulas, feedback conductance, base splitting resistance, etc. Okay, these are all the very important formulas, break capacitances. Okay, that's it. This is about the first unit. Okay, okay. Thank you and all the best.